This conference will now be recorded.
Welcome everybody to another OCP session. So today I will present about window of uncertainty, and no further ado, let's see if I can just put the screen up again. And Google presenter mode should work. Let's see, I need to switch the screen, I guess. I guess it's showing the other one, and then okay, yeah. You guys see the full screen?
Yeah.
I don't see
Yeah.
presentation mode. It's still in.
Okay, let me see.
We see a full
how can I
screen,
start?
but it's not in presentation mode. You can see all your slides on the left-hand side, all the other slides.
If I just take screen, I think that will do it, and then just go full screen. Yeah, that should do it.
Yep. Now it's
Okay,
presentation
so
mode.
please feel free, interrupt me anywhere. This is not even like close to be called like, halfway. So this is more like a proposal, how we want to approach basically calculation of the window of uncertainty. And yeah, half done, whatever. So like I look forward for your comments and feedback, and we have it all recorded so we can always reiterate on it and see what we can do. So the motivation is basically we want to have in like distributed applications, if they require to know how much the window of uncertainty is to adjust accordingly to what they have, we want to provide that dynamically. And also specifically speaking, like let's say in case of applications where they look for linearizability, this becomes a key because let's say you may just take advantage of the latency if the the error bound is, let's say, much less than latency, then you can just have instantaneously like a transaction as it arrives, just based on the fact that latency covered for that like jitter, the uncertainty, and then you can have always the linearizability criteria met. And also in parallel to serial pipes, when you have, let's say, completions of different completions, let's say in the parallel pipelines, and you want to, let's say, wait for all the completions to squeeze them in and go further in one serial pipeline, you can also look at the error bound and try to minimize, let's say, the error bound, or how much is it valid to, let's say, rely on this data that you're measuring based on this distributed time. Then that will basically be driven from the window of uncertainty that you have across all these machines. Also, the one-way latency, definitely you need to know how much you can rely on that, like what's the precision of this measurement, or even accuracy. And then we have like these other things, like for example, precision time-based scheduling and routing, where now you are trying to, again, minimize the variance for the delivery of all this, let's say, contributing machines in a network based on how much latency they see. Like for example, you have, let's say, 5 machines, and then they're like different parts of the data center, but then there is, let's say, a centroid where everything has to be collected there, or like there's an arbiter machine. What you can do is you can have those tasks that take longer on those machines that are closer, and the tasks that they take, let's say, shorter in the machines that are further, and then somehow like have the scheduling and routing now based on the time. But then You can't just assume things like, let's say, if they're under the floor noise, and the floor noise is again the window of uncertainty. And another interesting thing is like if you have the window of uncertainty continuously calculated in your system, that's actually a good indication of the performance of your system. So including oscillators, transparent clocks, the grandmaster, let's say the GPS, the atomic clocks, all of these things, they reflect back in the window of uncertainty. And then even like going a bit further than performance, you can do fault detection or prediction of fault. Let's say as you see something start degrading, you know, like, okay, this is probably going to hit, let's say, a major error or like failure or something. So it allows you to have some insight on prediction of how things are going to happen, like as you go forward. So what I'm trying to do in this presentation is like we'll go a little bit, just quick reminder on how basically time gets delivered to end nodes from the time server, and then how end nodes need to estimate and predict the error bound, and then the time server provides to the end node because the time server is also not the source of truth. The time server itself looks forward, let's say, via the GPS and all the things to let's say UTC, and that also has an error bound, but I mean sometimes it's trickier, like let's say because you don't have like a solid connection, all you have is the GPS, but we'll go through some numeric methods like this to look like how you want to estimate that as well. And then this is a again more of a proposal, it's not written on stone, that we want to have the error bound separated in two parts, precision and accuracy. And you see like there's a logic behind it, but again, it may apply to some applications and may not apply to others. And also the precision basically comes from how the variance of the the offset on the end user, let's say, is perceived, versus accuracy, which is more an agreement across like the whole network with other peers. So quick reminder about the accuracy and precision. So you can see the top row where you have like all the machines, all these clocks, completely random, scattered, whatever. So there is no accuracy and there's no precision. And on the right side, basically, far right side, you have the reference. The second one is you're bringing accuracy. So this is, let's say, in case of NTP, for example, right? Well, everything is kind of converging towards like that reference clock, but still the margins are very big. And opposed to this, you can have also not accurate but precise, where you see the changes between all the clocks is very small, but they are all off. They're not accurate, but they're precise. And then finally, which basically what we're looking for is we want to have precise and accurate. So they're all, the average is all around whatever the reference is, and there is not that much variation between all the clocks. Also, there is some classical formulation for all these things where the clock synchronization is considered a process, which it is, like on all the end nodes. And then every end node has the HC, which is a hardware clock. And there is the synchronization process, like which creates an adjustment. So the adjustment here is, let's say, it can be just an increment, or it can be an increment and a factor, which is like a linear factor. And once you apply the adjustment, you have a projection of HC, which becomes AC, like adjusted clock. So now the error bound is defined as gamma, which is the subtraction of any given clock inside the network, like adjusted clocks, basically. and basically the absolute value, that the difference between them. And now you can see that this is more of a deterministic way to describe it, but when it comes to reality, then you look practice, right? You apply it more in a statistical way. You look at like, okay, what in what, and as we go further, we'll see. Now, gamma itself can be described with an epsilon uh, minus basically epsilon over n, and this is basically somehow showing that like a sigma, and now you can have it in a symmetric distribution, like two pieces, like the one this side and one that side, the sum of them basically to create like that gamma that you're showing as the error. And again, you can consider this as a first sigma for your like formulation of the error. And then there is again some more mathematical framework for this, where now the difference, this basically shows the fact that now the adjust itself goes through another variation, which this variation is actually from the network itself. So like this is the challenging part of writing the control algorithms for like these time stuff, is like the network itself induces error, and then you are constantly going through like battling basically the entropy that you see on every system on like on this micro holdovers. As things are just going forward, error keeps increasing, and you're trying to like battle this error, but then network itself has also errors. Dealing with all error and error. So this is more like how you describe, like, okay, between two adjusted clocks, and you have the hardware clocks and the adjust, and then now every one of these errors, how they add up and sum up and so on. So now let's focus a little bit more on the estimation. And again, feel free, stop me if you have a question or something, we can discuss it. So for the precision, again, it's an estimation of precision. We are relying on the offset. So where is the offset coming from? Is the T1, T2, T3, T4 method in case of PTP, let's say, where, I mean, we've been through this, but just a quick reminder here. We have like the sync message from the time server going to the ordinary clock, and there is a causality problem here. Like you want to put in the sync message when it left, but then the sync message has to be departed, then you know when it left. So what you do, I mean, there is also the one way that, again, it's a compromise, but like this is like a proper way to do it, is like you send a sync message and you send a follow-up that says, hey, sync message departed at this time. But then you look for the arrival of the sync message, because now when you get the follow-up, you know when this specific sync message left and when it arrived, left the time server, and when it arrived to the ordinary clock. So at this time, you have the offset and the delay. So delay is latency. Offset is basically like the D of I and J, like basically difference between the two. This one. So now you have one side of, you have basically two unknowns, like offset plus delay, and you have one equation. So now you need to add another equation to make it two equation to unknown, right? So what you do is now from the ordinary clock, you send a message, delay request, to the time server. Time server doesn't really care when it departed, but you should keep it. So this is T3. So the moment the message arrives at the time server, that time basically gets sent back to you as a delay reply or delay response. And now that's T4. You have basically the other way. So now these two numbers, like basically the first one and the second one, if you add them, divide by 2, it gives you the delay, and if you subtract them, divide by 2, it gives you the offset, or vice versa. So Now that is basically what you feed into your servo, and that is basically telling you, hey, let's say you have I don't know, 200 nanosecond offset from the time server. So one way to do it is like, okay, let's just adjust 200 nanosecond, but you don't do that because, as I said, like the formulation, you see like the network itself is jittery, and the network itself over time, like basically on a distribution is, let's say, Gaussian. Again, estimate, it's all Gaussian is also an estimation. It's approximation, sorry. So now what you do is you feed that in a PI control, and the PI control starts handling like on the proportions and an integral for the long term. But now, before even adding it there, if you just look at the offset itself, you will see the distribution. And the more precise your system, that your network is behaving, the narrower you get basically this Gaussian distribution. So now, this error itself, like this Gaussian distribution, is reflecting what the NIC sees going across the network to the other NIC, because that's where the sync messages, like the delay request or response, like the sync and the follow, they go between the NIC of your end node and the NIC of the time server. But there are more things here that can go wrong. So the NIC itself to the time card to the GPS to the UTC, all of this is another system, and we can't just take it for granted and say like, okay, that's source of truth and take it from there. And then from the NIC itself, that's another thing out of the scope for this discussion, is like, now from the NIC itself to the application, you are going to have also some more, like, you know, sources for uncertainty. But again, the focus here is from this NIC to that NIC, what's happening, and then what are we getting basically from the NIC onward to, let's say, UTC. And one easy way, let's say, to sum all these uncertainties together is basically the law of total variance. So meaning you can really add the variances. Let's say if the time card toward UTC can calculate its variance, and let's say gives the variance alongside with, like, let's say the sync, all the operation for the sync and follow, delay request, the response, all of these things. And the NIC starts seeing basically how things are with respect to like the end node NIC, to the time server's NIC. It can calculate the variance, and it can add the variance that the time card is advertising as, hey, this is what I get like from up. So here is a good example of this is actually on the bottom left side. I have a screenshot from the Calnex Sentinel device showing in cyan an L1, L5 GNSS, and on purple is a L1, L2 GNSS. And you see that they are varying like somewhere, like the L1, L5 is like going all the way to almost 30 nanoseconds. And the L1, L2 is like about 10, 15 as advertised. But then the atomic clock tries to act as a filter and very stable, goes through like a lot of like filtering is happening there. So the atomic clock is really keeping things pretty much like sub nanosecond. So there is here definitely a reduced precision, but you may have accuracy. You may have a continuous offset that you get from the network. And so you can go basically between now, let's say, time cards, and then see, okay, what's the consensus? What are we seeing? If all of them are matching, then, well, looks like the atomic clock is doing well. So, and that really depends on if the distribution of error for the GNSS is staying, let's say, symmetric and Gaussian with no skewness or kurtosis, like where then now the average is really hitting on zero. So then the atomic clock is really like extracting like the precision with like minimized accuracy error. So now let's say that is all measured, like versus like the atomic clock you're getting and all this thing, you get all these estimation of the variance that you get on that side, so that you can push this further. Again, as I said, like with a message which is available in PTP, I think onward, like PTP 2.0 onward, like 2019. You have all of this. It's called variance at scale. So then now when it arrives to the end node, the end node can combine the variance that it perceives and the variance that is told, and it gives you like to the application, hey, this is the first sigma I get in terms of precision for my sync operation. So here we did a experiment. So we basically put the or time card with a time server, and then we used the CalNex Sentinel, but we fed the CalNex Sentinel with a cesium clock to just improve, because they like these SA53 like an SA55, these are really high-end oscillators. So if we just put them like they basically compete with whatever it's in the Sentinel device. So you see a lot of error between all of them. And how we figured out is like we put multiple of them, and we saw like when you see matching error between all the time cards, that means the reference is like basically going around. And we saw like they were all in the same range. So you really cannot have the Sentinel device with a built-in rubidium clock to come and like go in these like very precise measurements like with a time card. So what we did is that we put a cesium clock, and the cesium clock was used for the Sentinel device's external clock, and then everything went really sub nanosecond. Then things start become more stable. So what you see in blue is the PPS output of the time card on the time server. So it's also not perfect. Why? Because let's say the atomic, so you have the GNSS. GNSS has some offset on the whole process of GNSS, and then you have like in the time card the whole process of going to the time to like synchronizing the atomic clock. But as I showed you, like that actually can improve the precision. But then from the atomic clock, you need to discipline the PHC of the front end NIC, the NIC that is talking basically to all the other end nodes across the network, which basically the NIC that provides a sync, follow, the response, all of these things. And there is a servo there, which I mean, there is a tool called TS2PHC, and I think TimeBeat has it already built in Square, where you start steering your clock based on, let's say, PPS input. Again, it's the best if you can use like, let's say, PPS input, like from the time card you get PPS output, you feed it to the NIC. If you don't have a NIC that can do PPS input, you basically use the PCIe bus, but then again, you will have more of a compromised error just there before you even enter the network. So this is the offset that we really like to, this is a variance that we really like to feed into the network across, along with the packets, real time, to help the servos as they estimate what they perceive on, like in terms of variation on the offset, on the servo, they add this variance as well. So this gives them like a total variance like this. And you can see here in, I think you guys will see it's purple, gray. So this is the output for the NIC on the end node, giving a PPS output. And you can see like it gets much larger. And then we did like, I wish I had it here. So the standard deviation for blue was somewhere around 10 nanosecond, 10, 15, something like this. And then we had the servo itself, just from the offset, was perceiving, I think, somewhere like 60, 70 nanosecond. And then what we perceive on the Sentinel device was about 90. nanosecond, and that makes sense because this is the standard deviation. So square of like, I don't know, 10, let's say, plus the square of like 60, 70, whatever it was, root square, that was approximately putting us like around 90 nanoseconds. I don't remember, like I might be a little bit off on these numbers, but I have it somewhere else. I wish I was putting those calculations on the side. I think I presented this specific results in last that OCP General Summit last year. So another important thing to do before you basically take your stats and apply things to it is you need to basically look for the stationarity. So stationarity is determined by like what's the minimum size of a window you need to have in terms of your samples to apply statistics. You know, like this magic number, the 30, where you use this for central limit theorem, pretty much central limit theorem. Like you're looking for where, but this is for the variance. So now what you do is, this is, you have your data over time, the time series, and you assign a size, like this graph on the right side is showing that. You assign a size for a window that you screw. So let's say this is the formula, right? So, and you want to screw like n basically over your data to see at what size the variation starts going, let's say, below a criteria. Let's say I chose here 2%. And let's say for this PTP and all those things, we found that somewhere around 400, you start like wiggling around that like 2%, which was good enough. And that's like what we want to do. So here is also something you have to consider. You can't just put whatever size, make it very big, and then expect things to go down. Like there's a limit also that it will not go below that in terms of like variation. I'm pretty sure like other methods, let's say, I don't know, Allen variance or something, they can show you something similar, some similar results. So where, and also like that is the curvature basically of your distribution, which now there is another thing, the Cramer-Rao lower bound can also show you like how far you really can push on this. But we don't need to go that far. We will set a criteria, it's a 5%, 2%, whatever. And you want to have things around there because you don't want to go too far. You don't want to do data extraction. You want to keep a real-time process that is stationary at the same time. It's snappy enough, fast enough to respond to changes. Like imagine if I have, like, let's say a requirement of, let's say 1,000 or 2,000, 4,000, whatever numbers, and these numbers they get generated. That's usually once per second. Let's say if your sync rate is once per second, and that's like, I don't know, like an hour or something. At that point, you have, let's say, something bad happening in the system. It will take very long for you to observe this and report to your application. At the same time, if you have it very short, you may give like, you know, like unstable, like, you know, results all the time changing. It's a classic problem of like filtering. Like you want to push like the windows more to have like cleaner signal, or you want to have it like small and have like more changes or something. And there, again, smarter methods you can use. You can use like maximum likelihood estimation, things like that. So once you get that standard deviation or variance, you can use an assumption of Gaussian curve fitting, and let's say based on what the reliability that your system likes to, like your application likes you to calculate, you can present a window, and that's literally the window of uncertainty. This is the precision part of the window of uncertainty. So let's say you were doing like this monitoring the offset, and then you see in the offset that you're getting about like similar to what we had in that example. You're getting somewhere around 60 to 70 nanoseconds of variation. And then the like time server is reporting back, let's say, I don't know, 20, 30 nanoseconds also of variation that it estimates from UTC. Now you combine these two and you get basically the total estimation of error, like basically your variance that you're observing from here to all the way to UTC. So now if you want, let's say, this criteria of 1 in million P69, then you need to multiply that by 4.754. And why that number is because if you take an integral from the Gaussian bell curve, which that's a formula for it, you see that at that value, you will have this 1 over million. So now, let's say with those numbers that I presented, let's say instead of 90 is like, yeah, let's say 100 nanosecond, that's what we perceive. You announce 475, let's say, nanosecond as the error bound for P69. So what does that mean? It means that if you run, and again, this is an estimation, it's not a guarantee. No one can predict in the future. This is what your system is telling you, that based on the past observation, if you had 1 million, let's say, observations, less than, or I mean, let's say, if you want to be more like statistical, let's say if you had 10 million, less than 10 will be out of this bound, and that is what the application, the customer, will constantly receive, and based on that, they can adjust whatever they're doing. Is this good or not? Or like they can, let's say, degrade performance, shut down the service. It really depend on what the application is. On top of this, if you look at like what is really constituting the drift that you get in the clock, you see that the biggest contributor is the temperature changes that the local oscillator, every NIC, is receiving. So you may say like, okay, if that's the case, why not add it, like, let's say, some temperature awareness, temperature changes basically of the local oscillator. So then you can actually use the trend or the changes of temperature to do arbitration of, hey, are we really getting a, do we need to do like, let's say, a huge adjust here, or this is perceived from the network? And what this requires is it requires like you have a precise, it doesn't need to be accurate, a precise and stable temperature measurement of the local oscillator for two things. Like, one is you can constantly watch how the temperature is changing over time, and based on that you have a confidence on, hey, nothing really changed here. I mean, there is other factors like aging or whatever for the oscillator, but they're not going to be like so subtle and fast. So if that is going on, and the error bound I'm calculating from the past, so I'm very confident that this error bound is valid as I'm going forward. So that allows you to have, let's say, more response time when there's really a change, sudden change happening. Let's say some fans start, like, I don't know, like thermal throttle, whatever, fan failure, and that NIC, that system start getting hot. So it needs these like immediate changes, or the immediate changes, that's a separate thing, like the adjustment. The error bounds start like basically going off because the oscillators start being thrown off, and you have an error bound that is still laggy because it looks for the last 400 like values. So instead, when you see like temperature changes, let's say, you can reduce the window size, so you have like again, more faster response time, more agility, so you can like have the awareness going back in the for the customers before they, it takes them very long till they find, oh, this last, I don't know, whatever, 10 minutes or whatever, were all off because this thing was like, you know, still the error bound was still calculated. And also, this is like a little bit like icing on the cake. If you have that temperature aware, you can actually use this to improve holdover performance for that end node. Let's say when you lose connection with the time server or something, you already collected from the past for every temperature, what was the frequency adjust? Again, assuming that everything is repeatable and so on. So then you can start steering the clock now, steering the frequency based on the temperature changes that it sees. And again, like as I said, like it really depends on the application and so on, where you want to find a trade-off between how much you want to rely on what you observe versus what is the model. The model in this case is really the holdover of your clock. Like it's very interesting. Like let's say we use these methods like observation and model. Let's say in Kalman filter or something, where over there we have to have an entire, let's say, process to do the model. It means like the projection of previous data. In this case, actually relatively easy. Literally, don't change anything. That's your model, or like the values that you get from past offset and pointing out what temperature associated with every frequency change. That's your model. And then observations like what is new you're getting from the network on every sync session. So the second part, which is a little bit harder to like grasp because is more like theoretic, is the estimation of accuracy. So accuracy is an arbitrary thing. It's like, okay, let's assume, let's say the rate of the heartbeat is 1 second. And so now we use this as 1 second, while precision is really just the changes of thing, and they can be somewhere completely off, but as long as they're all like, you know, agreeing, that's precise. So how we approach accuracy, let's say, for this given problem, when you have like things in let's say a data center, is based on the linearizability test. So linearizability test is basically, hey, you send a message and you put in it the time that it departed, or like you keep it. You just send a message. Remember the sync message, like, or like the delay request, delay response. You do the delay request and delay response to a peer, not to the, let's say, time server. So you're sending a message to the peer, and the peer is going to respond back when this message arrived. So back in your clock, you have when the message departed, and you're receiving back when this message arrived based on the clock of the machine, of the peer, right? So you look and you see, is it like cause and effect? And that's linearizability. If it is, then you consider that as linearizable. If not, it's not. And I will show you now how we want to take advantage of this. So the estimation of accuracy, we were defining it as the estimation of statistical specificity. So it means how specific is it to find a machine or find a peer that is not linearizable. Means like that process that you do, you send a delay request and you get delay response. You wanna estimate how rare is it that I'm going to send this and comes back and I have like this cause and effect reversed. And this method is really optimized for a TC only implementation, all transparent clocks. But I mean, with some consideration or something, again, I didn't put enough thought in it. You can definitely include boundary clocks in this. And I mean, with the boundary clocks, you have the variance on each one of them as well. Like that variance at scale becomes a little bit trickier. So you need to probably look a little bit careful how you want to add that. And the feedback that you're going to get is for every node versus its peers. So it's a decentralized method. So if you want to have like a centralized overlook of how things are, you have to think about a way to basically funnel back everything now to a central node or somewhere, it's central database, so you can look at everything, how things are really working across the whole fleet. And also here, we're considering a scrolling like history for linearizability test. And how that works is, let's say you look for, again, you can really adjust it for whatever you have. There is also some, let's say, criteria, but nothing like stationarily here. So what you do is you look back, let's say the last 30 probes that you're asking different peers, and if they're linearizable or not. And what you can do is you can have a factor of, let's say, half if it was linearizable, and a factor of 2 if it was not, and you clip the whole sum, let's say, between 0 and 1 to keep it like statistics. So now what happened is, like I can just show you the scenarios, but before that, let's look at like how, like why we really are saying like this is specifically for TCs. So imagine this network, again, it's all TC, pure TCs, and you have these ordinary clocks at different, like, you know, branching, they end up, and a lot of things are string, just like for abstraction. And let's say all of a sudden these orange ones is that this orange transparent clock is a rogue transparent clock. So what's a rogue transparent clock? Rogue transparent clock can be either a transparent clock that is not filling the correction field, basically disabled or something, or there's an issue with a local oscillator of the transparent clock.
Wait. Can I ask you a question?
Yes.
This is a very unusual diagram. What's going on here? Why are the ordinary clocks speaking with each other? How is this mechanism?
No. So ignore the green and red on the bottom. You have, yeah, basically this, right? All transparent clocks, they go via, all ordinary clocks going via transparent clocks to the time server, right? Then you have that orange transparent clock that is rogue. And let's say either the correction field is not, like, you know, getting filled up properly, or the local oscillator, instead of, let's say, I don't know, 10 megahertz is like, I don't know, 200 ppm off or something, like whatever, failure or different, I mean, different part, whatever, it can happen. And all this subsequent chain is going to get affected.
Sure.
So yes.
So with this in mind, how do you know about this?
You will see in a moment.
Okay.
So now, even though, let's say, if the other transparent clocks, like subsequent transparent clocks, they are not rogue and they're doing their job, you still have the ordinary clocks with this induced offset, right? So now, this is the interesting part. Those affected ones, they might see each other all linearizable. Those like green and red, they're linearizability tests. They might see each other all linearizable. And then also, the linearizable is not only be above, it has to be within the error bound, because the pathway is a transparent clock as well. So you should know what the delay, what the precision is, and latency, because you have the delays. So you can add that. Or, I mean, in a simpler way, you're just looking for greater. And like, I mean, like if this one is ahead than the other one, and that should be also fine, because if it's too far, then the other way, like let's say too far in this way, then the other way will catch it. So because you have the latency acting as a buffer. So that island, all those machines, they might see each other good, but then when they check with other machines out there, then you have like the bad.
But they don't check with other machines out there. That's not the model here, right? The ordinary clocks do not speak with.
This is the model that you check with peers.
Right. Well, as you know, I'm quite a proponent of that model, right? I'm just this isn't.
You probably like something more centralized. So I'm just saying, if you are looking for accuracy, this is the definition of accuracy. Accuracy is like something that is agreed across the end nodes. That's why you have to look for peers. Otherwise, like, I mean, you can always derive something easier or centralized for this, but this is like the basis of it. So
okay,
now,
well, no one agrees with you more than I do, right? You know that. But what you're describing here is essentially PGP squared, right? it's not PTP.
Yeah. Of course. This is not PTP, but it can use PTP's mechanisms, you know. So
Yeah,
now
yeah.
I put like 3 scenarios. So first scenario, all the machines are in sync, all the transparent clocks are working, everything is good. So let's say, looking from the perspective of this ordinary clock 1, delay request is sent, delay response coming back from OC3, everything good, OC2, everything good, just keeps checking with every other machine, everything is good. And then you start having like basically these coefficients adding up. You have basically this great pie of all these coefficients. Number plummets, goes like close to 0 everywhere, because everyone is checking with everyone, everything is working. You have scenario 2, there is one or like very minimal machines that are getting bad, which I'm assuming this is more a realistic scenario. At this point, you're checking with this bad machine once in a while, you get a bump, you get a 2 instead of a half, and then with the other machines, you're still getting like good numbers still low, but there is no someone else problem. If there is one machine that is bad, either take it off or like don't, or fix it, because if it's there, then it affects like your distributed system performance, right? And third scenario is you're the bad one and you're checking with everyone else. And again, sometimes you may get extreme the opposite, right? But let's say you're failing on all these, and right, your numbers right away start going up, and you know, like, hey, it's not so specific to find disagreement. So that means you're the bad one. So now, what I was thinking we can even, let's say, do in this is you can the optimization for, remember I mentioned the optimization for the pure transparent clock is based on picking a random machine. Again, this can be also adjusted to different applications. Let's say if you have a pod of machines and all these machines are always working together and all you care is the accuracy across all these machines, well, instead of random, you have a pseudo random or just this list or just go sequential, check with all this pod. But let's say if you are really looking at random in the data center, you pick a random server, you go through this and everything is good or bad, instead of, let's say, 2 or half for coefficients, right? 2 for bad, half is for good. You can actually have a power of that based on how many hops you're away. So let's say if I get an agreement from the machine all the way on the left to the machine all the way on the right, that's great. That means like a big chunk of the system, because there were a lot of hops in between, right? Big chunk of these transparent clocks are on agreement. So that has more value than, let's say, I checked with my immediate neighbor and even if like there was something bad, like let's say in that route, we may have agreement, you know. So that's something, again, a food for thought can be applied to this to basically have like faster, like, you know, or slower, like it takes much faster to converge to, or like the effect of a bad machine or good machine can, like, you know, show much faster. And yeah, in conclusion, again, error bound, as I said, it's an estimation process. Again, no one knows what's going to happen in the future. You just look at the past and you estimate something. And then by scrolling like the past, again, you're basically relying on your observation. And then temperature, again, temperature or any other perturbation sensors, as I don't know, 10 cents are getting cheaper or something, like we may have like all kinds of things, like, I don't know, vibration, whatever. You can like use those to create some awareness for that estimation of, hey, things are stable, so most likely we're good for the next, I don't know, short period of time. Or no, things are getting crazy, so let's go, like, I don't know, closer and tighter on like estimation. And then this precision and accuracy, I'd like to hear more from Lasse, like separating them. What do you think? Have them separate, have them together, not necessary. I'm open to anything. Yeah, with no things.
I think it's absolutely right. And as you know, what we do in Squared is because first you did a section on precision, and what we do in Squared is we do not take the hierarchy for granted, right? We allow time flows to transition through nodes, and we optimize it not according to accuracy, but according to precision, right? Where we aim for the cumulative, let's say, the sigma of the standard deviations to be minimized, right? That's our strategy.
Yes.
So, I agree with everything you say. I think the crucial bit here is, let's say, why I get up in the morning is the understanding that this only works if ordinary clocks speak with other ordinary clocks. Okay, and
Yes.
for that one, yeah, I completely agree with you. Because making the assumption, let's say, as I heard you say early on in the presentation, that here we assume no asymmetries. Here we assume symmetry. I just don't know any networks that are like that, right? And so, but as you know, I rave against determinism, and I say, okay, we must, from second to second, measure and compare. How does the accuracy? How does the essentially precision is slang for variance, right? And accuracy is slang for the delta between means. But I agree with everything you say, as you also know.
So
Can I also make a comment, Ahmad
yes,
and
go
Lasse?
ahead.
I think one of the things that's important to bring up here is that this is all true as long as the ordinary clock recovery algorithm is the same across all those ordinary clocks. So all ordinary clock recovery algorithms are not created equal. The different manufacturers write their algorithms differently, and therefore the way they recover the PTP that's coming over the network and translate that into disciplining the local oscillator can be different. And so as long as all those ordinary clock recovery algorithms are the same, then yes, fantastic. But if you're using different ordinary clocks from different manufacturers that use different recovery algorithms, there can be differences there. So that's, I think, an important thing to keep in mind, that the recovery algorithm on the ordinary clock is one of the most important pieces of the accurate transmission between, source and, let's call it, endpoint.
Is this for accuracy or for precision?
I think it really is for both, right? I mean, it just depends on how good that recovery algorithm is.
Because I mean, regardless of what the vendor is or what algorithm you use, you should have the clock. Like, I see your point. Like, let's say, because this is like a peer thing at, like, it's a horizontal thing, might get affected. I know, Lasse, what do you think about that?
Yeah, I mean, again, I agree completely. So in Timebeat, right, we take this very seriously and act very unlike other, let's say, reference clients in that we implement we implement, let's say, what we call it a modified lucky packet strategy, right? So if we're running, and this takes into account essentially the various asymmetries as they occur from fractional second to fractional second, right? So if you run Linux BTP, it's not unusual that you make an adjustment every time you have T1 through T4, right? Whereas we make a big deal out of ensuring that when we make an adjustment, a steering adjustment, it is because the software recognizes a genuine offset between, let's say, the source of time and the consumer of time. And so if we run at 16 or 32 transactions a second, it's not unusual for us to make 3 adjustments in 20 seconds, and that's absolutely necessary because from second to second, the network buffer will have more packets in it, a switch will be busy, or if there is a conversion in the layer 2 part of the network, that's absolutely essential. So I completely agree with you, and it's striking, you know, how big a difference, how easy it is, let's say, in the part of the spectrum where clients have simpler algorithms, how easy it is to throw them off completely, and it takes 10 minutes for them to recover, right? Whereas, yes, we take quite a different approach.
I heard Leslie talk about BTB square. What is this BTB square? Maybe
I think was more like a joke referring to PTP, next PTP, right? Something like this.
yeah, I got it.
Okay, PTP squared is a system where on top of PTP, we build an overlay network, okay, based on a distributed hash table, where different ordinary clocks find each other and establish PTP unicast sessions between one another, okay?
But
And
this is described somewhere.
yes, it is. Okay, I built a whole business on top of this.
Awesome.
So let me post the.
Where I can find documentation about this DHT on top of BTB.
Well, you're literally like my PR guy. Firstly, there is an OCP tab presentation. Okay,
Yes.
this is where I give what I term the ambient presentation. Okay, where first I do a presentation for 60 minutes, and there's a demonstration that lasts for 30 minutes. So if one evening you have problems sleeping, okay, you can have a look at this. It's very, very effective at sending people to sleep. Okay, so I would recommend that. But I will post also in the chat section of this a link to a page that has more information.
Robert added it to the chat. Yeah.
Yeah, if you can put something in the chat, will be great.
It's not necessarily the most conventional system ever made, but at the moment it is capable of doing some stuff which is very cool and very useful. Okay, so not only does it evaluate different sources of time concurrently in ordinary clocks, it also allows ordinary clocks to receive feedback from other ordinary clocks about how the time that ordinary clock has distributed compares more globally. Okay, so it's not uncomplicated, but I don't want to hijack the thing, but I'll post some links.
Yeah, so let's see. You said you presented it in one of the tab meetings.
I have, yeah, for my sins, I have.
You can just
Okay.
find the number of it, just on the wiki, so you can say. Should be
Okay.
a thing.
Okay.
It's
Thank you.
very recent. It's this year, yeah. So Dan has asked the question about why only the ordinary clock and not TC. Well, the TC doesn't have any notion of the time. It's just relaying the ingress and egress difference that it sees from the packet as it's there. Well, the changes really show up, the effects, of rogue transparent clock, they show up at the end. I mean, you can make the transparent clocks like, check each other or something, but I mean, that's like you build on top of this. Like in the end of the day, accuracy is, even if I'm precise, I need to be in sync with these other peers. Like now, if you want to take it and flip it in a different way, build, let's say, a reverse grandmaster or whatever, sure, like this is the principle. I'm trying to explain like the basics, what we're measuring really. In the end of the day, whatever you measure is going to reflect what's the agreement between all these machines. You're muted, I think, Dan. The microphone. Typical microphone problems. So let's see, do we have more questions? Yeah, I think that's it. And then lastly, do you want to talk about the YouTube video?
And now this is the squared one. Do you mean the Gerling one?
Yes, I think no. You put here a YouTube link.
The YouTube link is for the previous squared
Yes.
the OCP tab one. Okay, I didn't want to pitch the Gerling one.
So it's It's presentation 33, right?
It is, yeah, 33 from the 20th of October, 21.
So Hisham is number 33. So, and then link is here. Message, anything from your end? Hearing none, I think everything good. Okay, so we are above the hour. So any more questions before we close up for today? Hearing none.
Yes, Ahmed, I think you should publish this in a paper.
Write this in a paper?
Yeah, you
yeah,
should.
yeah, sure. Sure, I will look into it. I'll actually reach out to you. Let's see if we can work together on this.
Yeah, absolutely. That will be
Sure.
great. Thank you very much.
Absolutely.
Excellent. Excellent.
Awesome. Okay. Talk to you guys later. Bye, everyone.
Thanks, everyone.